Hello everyone. In this video we will use the HPS ARM processor to communicate with the FPGA and we will need the my first HPS FPGA file that already provided by Altera, and in this project is used to demonstrate the implementation of blinking LEDs are connected to the FPGA, and we will control them using the ARM processor. So the first step we need to do is to unzip this folder, and after we unzip it we will get this here, and it has inside it two folders. The first one for the FPGA, which has the RTL design, and the second one for the HPS, which has the C code. Alright, so the first thing we need to do is to go inside this folder, and as we can see here, this is the entire project for the FPGA, and what I'm going to do is to open the SoC system.q pf file and connect the LEDs to the FPGA so we can communicate the ARM processor with the FPGA using the code that we have in the C. So as we can see here, right now we have opened the software and it loaded all these files inside it. So the first thing I'm going to do is to go from tools and run the platform designer. And right here we have this window. It's loading the HPS design, the SoC design that communicate the FPGA. So I'm going to open this .q system file. It has all the mapping memory that connects the LEDs to the FPGA to the ARM processor. So our first part is to create that bridge which connects the FPGA to the ARM. Alright, so right now I'm going to upgrade all this information here. So as we can see here from this window, it has the bridge here, the AXI bridge, which has all the component inside it, and this here we have the parallel input-output LEDs, which it has the address memory for it and the Avalon memory mapped slave, and then the external connections. So first of all, we want to make sure that this parallel input-output LED is connected to the bridge that connects us to the ARM. So as we can see here, it's already connected, the clock is connected, the reset is connected, the S1, which is the Avalon memory with the address memory of 000 ended to F, and the external connection. Alright, so it seems everything is correct because as we can see here, the clock is connected to the clock system, and the reset is connected to the reset, and the S1 is connected to the bridge where H2F LW AXE master is the clock that we need to connect the FPGA to the ARM or the HPS. Alright, so to add the pilots here, we can go here and just type to the IP catalog and type bio. We can see from the processor and peripherals, under the tab of peripherals, we see parallel bio FPGA. So I'm going to add one. Since we have 10 LEDs, so I'm going to change this to 10, and it's going to be started with 3F as told in the manual. So once I have all of this, and I will start to the direction FF. Okay. So once it's finished, it says here we have created the basic input, the parallel input output 0. So I'm going to change it and rename it here and call it view like which we have in the tutorial LED. Okay. So since I have here this one, so I will change it, rename. Alright. So I will just deactivate the ones that we have here just for demonstration purposes, and I will rename this to be LED 1, So I need to delete this. All right. Remove so I can name it correctly. Okay. All right. So the second thing we need to do is to connect the clock to the clock of the input here, and we collect the reset to the reset circuit. And as we can see here, all the errors went out. And the second part is for us is to connect the H2F low axis masters to the design. So as you can see here, I will go down, down, down. It's going to be here. Okay. So after I make sure everything is correct, the next thing I need to do is to export this to the bio export. All right. So after I've done all of this, the next thing I need to do is to make sure that it generates the template and all the requirement for the design. And this is here. Okay. So I will copy this in case I needed to add it to the log code. So copy, close, and after that I will generate the HDL code regenerated. First of all, I need to make sure that to create HDL design files for synthesis, Verilog, no needs to check, and I will leave, and I will not doing any simulation for this part, and I will just generate the system. So as we can see here, save system completed successfully. Once I close it, now it's starting generating the Q system file, which is generated by the design platform designer. And this is the main part that we need to connect the HPS to the FPGA. Without using this tool, we will not be able to communicate the design, the FPGA with the ARM processor. So right now I'll be done with the FPGA part. Then I will go and implement the software part, and this is what we call it core design when we use the hardware and software together to implement a system. So I'm just gonna wait for it. So once it's done, I need to update all the files inside the project using Quartus software. But basically we will not update anything because it will be already updated by the Q system by the platform designer tool, and the only thing that we need is just to run the design. So generate completed with warnings, and usually these warnings are related to the design itself, and they are not that big deal. So I'm gonna close this and click on finish. So once I finish it here, as we can see here, this is the system that we have right now, and it gave us this message. And just ignore this message because the system will be automatically updated with all the files that has inside. So I'm going to close. Right now I will run the design. And it's compiling right now. So if I get some errors, that means some of the Verilog files are not added to the system, so I will need to add them manually, and after that everything will be in a good shape. Good. So if we go here inside this file, as we can see here, it's already added by generating the system itself. It added this terminal to us, which is, sorry, this port, which is BioLED external connection export, and we are going to use it for the to link the lids. Another thing is to go to this SoC system V file, and as we can see here, it has all the ports that we need to run the design, and the most important things that we need to make sure it's available is the lid. Yes, this is the output wires. That's what I'm going to look for. It's gonna take like 10 to 15 minutes to finish the compilation. So I'm gonna stop here for a while, and once it's finished, I will come back again. Okay, so as we can see here, it takes more than 12 minutes to finish the compilation process, and most of the time it's taken in the analysis and later, and I'm just waiting to finish the assembler and timing analysis stages. All right, so let's start with the assembler right now. As we can see, it's done. The timing analysis. Okay, so the design took more than 13 minutes to finish. And if we go here to the compilation reports, we can wanna see the usage of the FPGA board. I will go to the filter and then to the resources section and resource usage summary. As we can see here, it took more than 2,200 logic utilization, which are the elements, and more than 3,381 lookup tables, beside more than 3,000 registers, and the IO pins 368 with the HPS peripherals. As we can see, it uses the clock reset, the S2F axis, F2S axis, which is the bridges that connects the FPGA to the HPS, and so on. And it takes 868 memory block to finish the design with 0 DSP blocks. All right, and from here we can check the maximum frequency that the circuit needed to operate. And as we can see here, it took more than almost 1 gigahertz to compile and finish the design. All right, and if we go to the netlist viewer, just to check everything is working fine. All right, so this is the design. As we can see here, the bio lids connections are connected to the lids, and the clock is connected to the HPS with the switches, and the HPS is RX data. Okay, which is good. Right now, I think everything is good. I will go and implement the HPS part. All right, so I'm going to run this C code, which it has inside it. This code, which is connects the H2P adder to the memory, which is virtual base, as we can see here, and then it will display the result on the lid after a condition that the loop counts is less than 60. So if the lid direction 0, that means it will shift it to the right, and if it's one, it's gonna shift it to the left. All right, to compile this code, I will go to my system code, and I need to go to cd c until FPGA 20 embedded. All right, so if I go to this, I will run the embedded command shell. Okay, good. So my next part is to run the GCC and compile the C++ code. Okay, so I will go to cd C. I save it in the users. I cannot do it from here, so that means I need to move on. Users, the user downloads inside my first FPGA base, and the file list is gonna be inside my HPS. Yeah, so if I list it, as I can see here, the HPS. I'll go inside the HPS. Sorry for that, but this is what I got. So if now I will implement the C code. So once I press make, as we can see here, it generates for me the binary code that I need to run on the Linux system for the ARM processor. So if I go here, I will see this file which is generated right now, and my next step will be taking and copy this file to the USB disk drive and run it on the ARM processor. So the next thing what I'm going to do is to run the FPGA board and then run the Linux installed in the SD card, and I'm gonna do that in the library, and I'll show you in the next part of this video. So before I do that, I need to run and delete everything, and I'm gonna start from this point in the next part of the recording that I already did in the lab. So after I finished compiling the design and generating the SOF file and compiling also the C code and generating my first FPGA HPS binary file, I'm going to implement it on the FPGA part and here on the ARM processor part. So first thing I need to do is to copy the SOF file, the binary file, this one. I'm gonna copy it and paste it in the USB drive, and I'm going to take the USB drive and stick it in the FPGA USB port. Sorry. Alright, so right now I'm going to log in and fdisk/l, and as we can see here, this is the div. I will mount it to the USB drive folder. If I change the directory, as we can see here, this is my first HPS-FPGA binary file. So before I implement it, I need to go here to this part and upload the SoC file to the FPGA. So when I click on start, the screen will disappear, and that means the SoC file now is ready on the FPGA board. I just need to press on enter to see the LEDs blinking and shifted from the right to the left and vice versa. So once I click start, so the screen is disappeared, and this is successfully 100%, and as we can see here, the blinking. So once I press on enter, we can see the LEDs are blinking from the right to the left and vice versa with a 100 millisecond delay. Yeah, and that's it, and thank you for watching.